Hi, this is Raimu, and I'm here to talk today about TCP/IP and sockets. So hopefully I will be able to explain a little bit more than you might already know about what is the Internet Protocol and what TCP and UDP and sockets are all about. This does not require too much previous knowledge, just a general idea about what computers are and how they're connected on the network, you know, with cables and tubes. Anyway, let's dive right in. The Internet Protocol. This was designed many decades ago to connect computers together. Now, one thing that's important to understand about the protocol suite in which the Internet Protocol is one of many is that these network protocols, they form a stack to handle different aspects of the work. And, for example, this is our application, us. That's their application, them. The idea behind the network is that you are connecting different computers together that are geographically distant. Network stacks are used to take a message we want to send and pass it across the scary internet. Now, the different levels of the stack handle different things. So we have here represented on both sides the network layer and the transport layer. Internet Protocol is a network layer protocol. So remember that as we go through this. Let's say that this is a message we want to send. Now, messages are also known as datagrams, segments, and by other words. So when you see any of these words, it really just means a message. So in the case of Internet Protocol, they define the messages to be datagrams. Sort of a cool word, I think. Anyway, we have this datagram, which is really just a short message we want to send from our app, from the sender, to their app over in the receiver. This is the sequence of events. This message gets sent up the protocol stack. The transport layer, and this is what we'll talk about soon, TCP, UDP, that kind of thing, will attach headers. Headers are like envelopes. So each layer of the protocol stack attaches its own headers to insert the information that it needs to safely transport and deliver the message. So for a transport layer, usually it's port numbers. You might have heard of these before. They map numbers to individual applications. So the sender app has its own port number as a sender, and the receiver app on the other end will have its own port number that's probably different for its end. So the transport layer attaches these port numbers, and here's the key concept, that every time something is attached, it's sent up the protocol stack. So above the transport layer is the network layer. This is the Internet Protocol in our case. Internet Protocol attaches IP addresses for its header and is able then to, through other lower level layers like Ethernet or Wi-Fi or cellular, it's going to get that packet, that datagram, over to the receiver. And key to that is the IP address. That identifies the computer or the node of the network that the receiver has. When it gets there, it's going to traverse the stack in the opposite direction from the sender. So it'll first hit the network layer on the receiver, which will say, hey, that address is us. So sounds good. We're going to receive it and then send it up our end of the stack here. The transport layer then says, okay, I know what that port number is. It goes to this receiver app. Then the receiver app gets it, minus all of the headers, and says, we got the message. They said hello. So that's essentially how the network and transport layers work in the context of Internet Protocol. It is using IP addresses. Okay. Now a little bit deeper into the Internet Protocol. I talked about datagrams. Datagrams can't just be any size, because there are going to be computers throughout the network which can't take large datagrams. They have limits. So let's say we have this large datagram we wish to send, and now for illustration purposes, just pretend that 5 characters is large, and that the router in between there is very stingy and can only fit 1 character at a time. Your packets must be this small to pass through my network. So what we're going to do on the sender end, and IP supports this, is splitting up a datagram into smaller fragments that will each fit the network. Then transport them individually across the network so that they fit along the way. And when they get received on the other end, they're going to be reassembled by the receiver to reconstruct the original datagram that the sender started with and then deliver it up to the application. Okay, now we're going in deep. Now, don't let this scare you. I talked before about how each layer of a network protocol stack has headers. This is it for the Internet Protocol. There's a lot here to digest, but I'll go over some of the key points. If you really want to get into all the gory detail, just look up the RFC for the Internet Protocol, basically the standards document that describes the protocol in detail. So some of these things might make sense right away, other things might be more esoteric. One thing I want to talk about is the version field. This is a 4-bit field. It's the first 4 bits of the header for Internet Protocol. It identifies which version of the Internet Protocol this is. So for example, IPv4, it'll be, you guessed it, 4. If it was IPv6, it would be 6. Easy peasy, right? All right, here's where our IP addresses actually get stored in the IP header. So they're both 32 bits. Now you might have gotten familiar with the dotted decimal format like 127.0.0.1 and like 10.0.0.5, that kind of thing. In that dotted decimal format, each number is 1 byte or 8 bits of this address. So if you take out the dots and then convert it into binary, you fit it right here where it says source address, it's our address, destination is their address. Just like an envelope, you would put your return address and you'd put the destination address on it, right? Type of service, we get into more of the interesting detail here. The type of service is a field that is used to indicate what do we care about in terms of, do we want reliability in delivery or do we want fast delivery? It's also known as quality of service. Not to go into too much detail, but there are bits and pieces of the header here that are less frequently used, but they're still important. Time to live. This indicates how long we should try to transmit this packet from one place to another. The internet is full of a lot of routers. Sometimes packets get lost in loops and they can't make it to the destination for whatever reason. Time to live is used to make sure that we don't have packets that just consume bandwidth on the internet even though they're never going to arrive correctly. Essentially, it's a counter, and every time the packet goes from one computer to another, we subtract 1 from that counter. If the counter reaches 0, the router says, it didn't make it, so just drop it. Header checksum. You'll see this in a lot of internet headers. It is basically a guard against simple bit errors. So if there is a corruption in the packet, what would happen is the checksum, when it's compared to the rest of the packet, wouldn't match. More technically, what it is all of the bytes of the header are added together, and then there's a little bit of a transformation done to the sum, and then it's stored into the field here in header checksum, so that if you were to do the same calculation on the receiver end, you could compare and make sure the checksum is correct. If checksum isn't correct, like it should be, when it gets received, you know that there was some damage to the packet and you generally just drop it. Okay, options. IP supports a lot of extensions, and one important one is security. So it's called IPsec or IP security. It is handled through the options. Options allow you to attach additional data to a packet or a datagram to enable some of those features like security. I'm not going into the detail of that. Of course, you can look up the RFC for IP if you want more. And that's pretty much it for what I'm going to cover here. There are some other things in there like fragment offset and flags and protocol, and they're not as important. If you want to know more, again, look up the RFC. But essentially, the job of this header is to identify what version of the Internet Protocol we're using, who's the sender, who's the receiver, how big the packet is, what the checksum is so that we can detect errors. And that's pretty much it. All right. One thing I should mention about the Internet Protocol, it's a best effort delivery, which means your packet might not get there, and if you sent several packets, you might not have them arrive in the same order in which you sent them. Here's an example. Dramatized example, of course. But let's say we're sending 5 packets across this network. Strange things can happen when traveling the internet. Oh, what happened there? We only got 4 packets, and they arrived out of order. Oops. So it's the job of other higher layer protocols to counteract issues like this. These issues arise, not that there are malevolent routers out there in the internet, but it's more typical that you'll have very, very optimized routers along the network that if there's any problem at all, they just drop the packet and move on so that they don't spend too much time handling one packet. So to compensate for that, you might have to retransmit a packet. You might have to make sure the packets are put back into their correct order. You might have to put sequence numbers in there. So this is the job of higher level protocols. So we'll get to that. All right. Transitioning now from the network layer to the transport layer, this is one level higher towards the application layer. So we're talking about on top of IP. Now, in memory, a packet would have the headers from the bottom of the protocol stack is at the top of the packet. So you see their IP header is above the UDP header. So meaning first in memory is the IP header, and then after the IP header is the UDP header, and then after that is the stuff that's being transported, right? What we call the payload. So having already an IP header, we know which computer sent this packet and which computer is supposed to receive it, but we don't know which application it's for. UDP adds this information. A port number, or a 16-bit integer, on both ends. Basically, it's a mailbox. It says which application from that IP address sent this packet and which application on the destination is supposed to receive it. So you can think of an IP address identifying an entire collection of applications that are running on a computer. A port number identifies which specific application. And even an application could have multiple ports. It frequently happens, right? So you can think of not only does the source destination port identify an app, but it identifies a specific session within a specific app, usually. But that's pretty much it. There's the source and port number. There is the length of the payload, and then another checksum. Yep, that's it. Pretty simple, right? And not much is added onto IP by UDP other than these port numbers. Now let's get to something a little bit more complicated. The Transmission Control Protocol. You might have heard of this, TCP. It's the TCP and TCP/IP. It handles taking a sequence of packets and making sure they arrive correctly and in order. So we talked about before, best effort delivery. Sometimes you lose a packet, sometimes they get out of order. TCP essentially is designed to undo those effects and get you to where you can send a string of bytes from one place and receive a string of bytes on the other end and not really have to worry about did any of them get lost or did any of them arrive in the wrong order. Basically, what TCP does is it breaks your message up into smaller parts. They call them segments, but you could also think of them as packets. It's going to attach headers to each one, and amongst the headers there are things like sequence number and other symbols and other flags. And the sequence numbers, for example, are used to make sure that you get things from one place to another. So imagine this sequence where the sender sends the packet marked with 6 and the receiver receives it. So it sends back an acknowledgement saying, hey, yeah, I got packet number 6. Then the sender says, oh, cool, let's send them the next one, which is 10. And the receiver doesn't get it. So that dotted dashed line means didn't make it there. So after a while, this receiver says, hey, the last one I heard from you was 6. Then the sender says, okay, they didn't get 10, so let's send it to them again. We're going to retransmit it. This time the receiver says, okay, I got sequence 10, so I can acknowledge that. I got it back, right? The sequence numbers and the acknowledgement numbers match. So each side is sending both sequence numbers and acknowledgement numbers because it's a bidirectional communication. There's a string of bytes going from left to right and one going from right to left. Now here's where we get into the scary diagrams. Now I don't want to cover this in too much detail, but just from a very, very high level view, Transmission Control Protocol involves the state machine. Now the state machine primarily is interested in tracking whether or not you're connected. So as you might imagine, the very first state that you start in is closed. Then you're going to go to one of the partially open states. So there's the passive open and then there's the active open. This depends on whether you're a server or a client. Servers passively open. They listen for connections. Clients, on the other hand, are actively trying to make a connection. So they will go to a state where they're starting a connection. Now, the beginning of a connection in TCP has to do with a handshake between this client and the server. The handshake is in the form of a special symbol called the synchronize or SYN signal. You can think of it as a special byte that goes right in front of the first byte of actual data you want to send. So just like normal bytes in a TCP string, they need to be acknowledged. So when you're, for example, in the SYN sent state, that means you're a client and you sent the SYN, the synchronization byte. You're waiting for the server then to acknowledge that it received that. And there has to be a reverse, that the server, once it receives that SYN, it's got to send back its own if it's accepting the connection. So while the client is waiting for the server, they'll sit in SYN sent. When the server acknowledges that SYN and sends their own SYN, then the client will go to established and acknowledge the server SYN. Established is the working state where both ends are sending bytes. You know, your application is running. The server does a similar concept where it's sitting in the listen state, and when an incoming connection comes in, they receive the SYN. They'll send back a SYN and an ACK, and then wait for the client to acknowledge their end. So this is a handshake. So you go from listen to SYN received, and then go to establish once the client is acknowledged their end. So that gets us from closed to open. How do we get from open back to closed? So from established back to closed, basically if either end wants to close the connection, they'll send another special symbol called fin, which means fini. It's the final or the last marker of the stream. Interesting thing about TCP is that since it's bidirectional, either end can close while the other end remains open. So you back into this half-open state. For the end that's done, waiting for the other end to finish, you will go to the fin1 state. Basically, you've closed your end, you've sent your fin, but you haven't yet received an ACK for your fin, and you haven't received the fin from the other end either. So while you're in this half-open state, you can not send any more data because you've already sent your fin, but you can receive more data. At some point, the other end will finish too, and they'll send their fin, and then you go into this special time wait state, which is really there just to make sure that everything gets cleaned up and there's no more packets traversing the network for this connection. Basically, the dust is settling in time wait. After a fixed amount of time, which happens to be 4 minutes, we transition naturally back to closed, back to the original state. So then the closed wait state is the other end where you're still wanting to send data, but the other end is done. You'll receive this fin, and you'll say, okay, I acknowledge your fin, but I can still send you more data. When you're done, you'll send your close and your fin. You'll go to last ACK where you're waiting for the other end to acknowledge your fin. Once that happens, you immediately go to closed state. There's technical reasons why through one path you have to sit in 4 minutes in time wait, and the other path you don't. And I'll leave that. But basically, everything ends up back into closed. It's just that the connection can be half open for a while, where one end is done and the other end is not. Anyway, if I haven't scared you away with that slide, let's talk about the actual headers in TCP. So just like UDP, TCP has those port numbers. They're also 16 bits, just like UDP. You have both the port number identifying the sender and the port number identifying the receiver. Again, they're like mailbox numbers, and they identify the connection so that looking at one packet, you know who sent it and where it's going. The sequence numbers and acknowledgement numbers I talked about before, they are used to put packets in the right order and to verifying that the other end received it. So each end will, when transmitting, attach a sequence number saying, where in the sequence of bytes this packet belongs. And in addition to that, also send the acknowledgement number from the other direction. So we'll say, for example, this is my sequence number 5. From you, I've received up to sequence 10. And the other end will say, okay, my sequence number is now 11, and I've received up to your 5. So it's both directions, and each one has a record of what number it's on and what number it's received from the other guy. Window is a little bit more complicated. The lengths or the sizes of packets have different effects on the internet. So, for example, a smaller packet is more likely to make it across from one side to the other, because there's fewer bits to be damaged and less need to fragment, but also kind of restricts the bit rate that you can send, because for every packet you got to attach headers and you have to wait for acknowledgement and that kind of thing. So in order to get high bandwidth with TCP, the window is used. The window basically says how many bytes we're able to receive. And as the window starts small, that means we can only send small bits of data. After the small windows of data are filled up and the receiver says, yeah, I'm getting the data, it can increase the size of the window. And then the sender can send more. The window also is a way to flow control. So let's say you've received a bunch of data and you filled up your window, but the application is sort of slow and hasn't caught up and received all of the things that the protocol stack has. It's a way for the protocol stack to say, hey, wait a minute, we can't receive any more data, our window is full. And then the sender on the other end will say, okay, fine, I'll wait for a while. And then when the receiver app finally consumes the data it's received already, it can, in its next message back, say, okay, our window is open again, you can send us more. So it's both a way to flow control to stop the other guy if you're not ready to receive more, and through the means of increasing window sizes, it's how we control making the connection faster or slower to compensate for, higher or lower bit loss and capabilities of the network connections between. All right, there are flags in here, and one of particular note is called the push flag. This is used in conjunction with the window to basically say, okay, everything I've sent, you need to deliver it before I can send you more. It's basically push it up to the app. And it's used a lot in interactive connections where before you can receive the next thing, you would like the sender to finish sending. There are other fields in here. There's the checksum, there's urgent pointer, there's options. Again, the devil's in the details for that, but I've covered the most important things, I feel. All right. Now we're going into the sockets. This is, again, one level up. So this is where, as a programmer, you begin interacting, in most cases, with networking. Sockets represent the application's portal, or the access point, or the API, into all the protocol stack stuff that we've talked about so far. So this is actually how you would use POSIX or BSD sockets, and also WinSock, which is very similar. It's based off of Berkeley sockets anyway. They're all the same kind of thing. Socket is a function which you can call to create an endpoint, whether it's using one protocol or another. You identify the protocol suite or the address family, which these days are the same thing. You basically saying, I want to use IPv4 or IPv6. And then the type of the socket determines whether or not we're using a connection-oriented, reliable byte stream like what's used in TCP, or just a lightweight, not as much overhead, but maybe not as reliable protocol like UDP. So once you get a socket, it's like a file handle, but you don't use the traditional read-write functions with this kind of file handle. Instead, you use a different set of functions depending on which role you're going to have in your program using this network interface. So for connection-oriented sockets, this is TCP, the reliable byte stream. I talked about there are very different parts of the life cycle of the connection depending on if you're a client or a server, right? So if you are a client, you're going to be using connect. This is how we establish an outgoing connection to a server. The first argument of all these functions is the socket. So you can think of these as socket methods. For connect, what you're telling the socket is, I want you to connect to the server at this address. And we use this sock address to represent the IP address and port number, essentially. Now, if you're a server, it's flipped around. Instead of actively connecting to a server, you're going to passively wait and listen for clients connecting to you. And this is a two-step process. Listen is called to set up the socket to start listening, basically opening the shop door, right? Accept is what you're going to call whenever you've detected basically a client incoming connection and you want to complete the connection. Now, the way that you know when to call accept it's a little bit detailed. We'll probably cover that in the next video. Essentially, after you listen, you can then tell the operating system to signal you when it's ready for you to call accept. Every time you call accept, you're connecting to a different client. If there's no one trying to connect to you, accept doesn't return you a new socket, right? Another side thing to mention here is that the socket you use with the listen and accept is kind of like representing the open port number for the server. The socket that you get back from accept is going to be just that server's connection to that one client. So you start with one socket, which you use with listen and accept, but every time you call accept, you're going to get another socket, which represents that client server connection. So if 10 clients connect to your server, you'll end up with 11 sockets, one representing the original one you used with listen and accept, and then 10 others that you got back from accept, one for each client. And they each would have a different life cycle. Now, whether you did connect or whether you called accept and got a new socket as a server, the one you're actively using to talk to the other end is what you're going to use with the send and receive functions. These are the socket equivalents of read and write. Send is like writing data. You were sending it, right? Receive, we're reading data, receiving it from the other end. In both cases, since it's connection oriented, we're talking about strings of bytes. So you have buffers in and buffers out, and lengths of those buffers. And the operating system will handle converting these send and receive calls into the using the actual protocol. Like for TCP, it's cutting them up into segments, doing the send, the sequence numbers and acknowledgement numbers and all that, doing retransmissions for you. And so you don't have to worry about it once you've sent a buffer to the operating system. You basically rely on the OS to deliver it to the other end. Now, what is shutdown? This is what I talked about earlier, the half connection stuff in TCP. When you're ready to stop sending or receiving, but you want to keep the socket open for the other guy to send or receive, that's where shutdown comes into effect. The how here is basically saying what kind of shutdown you want, a read-only shutdown, a write-only shutdown. The socket is still open, but it's only half open. So if you shut down the socket for writing, you can still read data from the socket, but you can't write anymore. The final close of the socket is what you do when you just want to give up on the connection entirely. So basically, if the connection is completely closed from both ends, you would just close the socket. All right. Now, I talked about connection-oriented sockets in the last slide. This one is talking about datagram-oriented sockets. It's much simpler. There's no state, there's no closed or open, and instead of a string of bytes that's reliably sent and received, it's more Wild West. It's like, here's a datagram, please send it. And then you just have to kind of like hope that it gets there. Or maybe you have a protocol on top of this which detects whether or not things you send actually got received and, you know, sends back a message saying, please send it again, that kind of thing. At this level, for sockets, it's very simple. You say, here's my socket, here's my message. Please take this message using this socket and send it to this other guy. And then receive from is the other end of that. It's like saying, I'm ready to get some data from anybody in the network that chooses to send to me. So here's my socket, here's a buffer where you're going to put it, here's another buffer where you're going to tell me who it came from, and then if you get something, good, here it is. If not, sorry, try again later. It's very, very simple. I mentioned and showed in the previous slides this sock address. This is a little bit of detail to kind of connect together some of the concepts. So socket represents the program's API into all the protocols. Sock address represents the addressing information. So the IP address, the port number, that kind of thing, are all stored in this sock address. Now it's sort of defined to be a generic type that needs to be specialized for the different protocol families. So the generic structure sockaddr can be specialized with sockaddr_in for internet. That is when you're using the socket with an internet protocol, as opposed to, let's say, a Unix domain socket, which is not internet at all. If it's an internet socket, then you'll use the sock address internet structure, which has the port number and the address. And then one final thing. You'll see in the next video, and if you see in other examples, the concept of socket options. This enables sort of like extra features with sockets. Depending on how you're using them, they can control various aspects of them. For example, the linger option is to tell the operating system what should I do with the data that you've given to me that I haven't delivered yet once you call close. So if linger is on, basically you're telling the operating system, keep the socket open at the OS layer, even though the app's given up on it, but keep it open in the OS layer to continue trying to send that last bit of data. But if the linger is off, you're saying like, okay, operating system, if once I close, then just throw it all away, even if you haven't finished sending it. Okay, another example, the no-sig pipe, that's Linux specific. There's a special pipe signal that can be sent in certain circumstances. And this socket option is basically telling Linux, I don't really care about this SIG pipe signal, so don't bother sending it to me. And then my third example here, the reuse address option for a socket, is telling the operating system to loosen its restrictions a little bit. Normally, sockets have to be one socket per address. So if you have port number 80, there should be one and only one socket that uses port 80. But if you turn on this reuse address option, you're basically telling the OS, I can have 2 or 3 sockets that I'll talk to port 80, and I'll deal with the consequences if there's a little bit of ambiguity. And so you have to be very careful using the socket options, understanding how they're used. So look up the documentation for them, etc. For normal, simple connections, you don't really have to set any of these options. They're more for special cases. And last but not least, the blocking versus non-blocking modes. So there are essentially 2 philosophies in data input-output with sockets and files in general in Unix. And those are blocking or non-blocking. So what do you want to have? You want to be blocked? You want to be not blocked? Blocking mode means that when you're trying to send something, you want the function call to not return until it's done, until you sent it. Non-blocking mode says, try to send this data, but if you're not ready, return right away and just let me know that you weren't ready. So personally, I prefer non-blocking mode because it allows my code to try to send, and if it's not ready, we return immediately, and then just try to do something else. Maybe we try to receive, or maybe we process some background stuff until we're ready to try sending again. But there are those who prefer the blocking mode. Basically, I just want to send this packet, and I don't want to do anything else until it's sent, so please send it, and don't come back to me until it's done. The way you turn a socket between blocking and non-blocking modes, it's different between POSIX and Windows, but on POSIX, you use the fcntl, which is the file control function, and there's a special mode called getting the flags of a file handle, and for a socket, one of the flags is the O non-block flag. And so turning it on in this code example here will change the socket to be non-blocking if it was in blocking mode before. So in Windows, it's a little bit different. I'll go into that in the next video. But essentially, you have to recognize when your socket is either blocking or non-blocking because it changes the semantics or the behavior of those other functions I talked about, like send and receive. Right? It's either going to not return or return right away, depending on what mode you're in. So in the next video, I'm going to cover specific code examples for how you use the socket API in the context of TCP and UDP to send messages from one program to another, whether it's on the same computer or on different computers, geographically distant on the other side of the world. So I hope you will watch that video, and thank you for watching this one. Hopefully you got a little bit better understanding of, at the high level and at the socket API level, how computers send messages using the Internet Protocol Suite. Thanks for watching.